Hi, welcome back to my class in differential equation. For today, we will take up one method for solving ordinary differential equation. And this method is called separation of variables. For those of you who missed the first two lessons in differential equation, please search for my first two videos on differential equations. Art teaches differential equation. Now, what is meant by separation of variables? Consider the following ordinary differential equation in general form. This differential equation is called an ordinary differential equation because it contains derivative and it contains ordinary derivative of y with respect to x. In this given ordinary differential equation, first order differential, this is a first order ordinary differential equation of degree 1. It is a first order because the highest derivative of y with respect to x that appears in this differential equation is 1. And the degree of the first derivative of y with respect to x is 1. So this differential equation is ordinary differential equation of order 1 and degree 1. You can see that in the coefficient of dx, we have a function of two variables x and y. Similarly, in the coefficient of the differential of y, we have a function of x and y. Now we say that this ordinary differential equation has variables that can be separated if we can write this differential equation in this form. After separation of variables, if this differential equation can indeed be solved by separation of variables, we should be able to write this differential equation in this form. F of x dx plus g of y dy. There should be dy is equal to 0. Again, if the given differential equation can be solved by separation of variables, the given differential equation can be written in this form: f of x dx plus g of y dy equals 0. After separation of variables, the coefficient of the differential of x is now a function of the variable x only. Hence, the first term can be integrated with respect to the variable x. Also, after separation of variables, the coefficient of the differential of y is a function of y only. Hence, the second term can also be integrated with respect to y. And of course, the right-hand side can be integrated, which gives us a constant after integrating 0. Now we take an example to solve an ordinary differential equation of order 1 and degree 1 by separation of variables. Example solve. To solve a differential equation is to find an equation whose derivative, first derivative with respect to y, first derivative of y with respect to x will give this equation. Again, to solve this differential equation is to find an equation whose derivative is equal to this. Whose derivative with respect to y, whose derivative of y with respect to x will give this differential equation. The coefficient of the differential of x is xy, and the coefficient of the differential of y is quantity x squared plus 2 multiplied by y cubed. If this differential equation can be solved by separation of variables, we must make the coefficient of the differential of x a function of x only, which means that we must remove y from the coefficient of dx. Similarly, if this given differential equation can be solved by separation of variables, the coefficient of the differential of y should be a function of y only. But you can see in the given, we have a quantity x squared plus 2 in the coefficient of dy. Thus, we have to remove x squared plus 2 from the coefficient of dy. If this equation can be solved by separation of variables. After separation of variables, the coefficient of dx must be a function of x only. The coefficient of dy must be a function of y only. And after separating the variables, the solution can be obtained by integrating both sides. The first term we integrate with respect to x. The second term we integrate with respect to y. And we integrate 0, which gives us a constant. We solve this differential equation by separation of variables. We can remove y from the coefficient of the differential of x or dx if we divide both sides of the given differential equation by y. If we divide the first term by y will be removed from the coefficient of the differential of x. But we also have to divide the second term and the right-hand side of the given differential equation by y. To remove the quantity x squared plus 2 in the coefficient of the differential of y, we can also remove x squared plus 2 by dividing the whole equation or dividing both sides of the equation by x squared plus 2. If we divide the second term by x squared plus 2 will be removed from the coefficient of the differential of y. But we also have to divide the first term and the right-hand side by x squared plus 2. Thus, we divide the whole equation by the product of y. To remove y from the coefficient of dx, multiply by x squared plus 2. To remove x squared plus 2 from the coefficient of the differential of y, we divide each term and the right-hand side of the equation by the product y multiplied by x squared plus 2. And we do that. The first term is xy dx. We divide by y multiplied by x squared plus 2. The second term is negative or minus x squared plus 2 multiplied by y cubed multiplied by dy. And we divide this by the product y multiplied by x squared plus 2. The right-hand side is 0, but we also have to divide 0 by y multiplied by x squared plus 2. But if we divide 0 by any quantity, we get 0. Thus, the right-hand side of this last equation is 0. Now, we cancel from each term of the left-hand side the quantities that can be cancelled. We have y over y is 1. Hence, we can cancel y from the numerator and y from the denominator. In the second term, we have x squared plus 2 in the numerator and x squared plus 2 in the denominator. And this quantity divided by the same quantity gives us 1. Thus, we can cancel x squared plus 2 from the numerator and from the denominator. Hence, the coefficient now of the differential of x is x over x squared plus 2, which is of this form, f of x dx, minus the second term. The coefficient now of the differential of y is y cubed over y, which is of this form, g of y dy equals 0. We now find, we can still simplify each term of the left-hand side, and then we find the solution of the simplified differential equation by integrating both sides. The left-hand side, we integrate the first term with respect to x, and the second term we integrate with respect to y. After separation of variables, we obtain the following differential equation. We have x dx over x squared plus 2 minus y cubed dy over y equals 0. But the second term can still be simplified by applying property of exponent. We have y cubed divided by y is y squared. The second term is minus y squared dy equals 0. The first term remains the same, x dx over x squared plus 1. Now we say that the variables have been separated because the coefficient of the differential of x is now a function of x only, and the coefficient of the differential of y is a function of y only. Thus, we can now obtain the solution or general solution of this differential equation by integrating both sides. The first term we integrate with respect to x. The second term we integrate with respect to y. And the left-hand side we integrate 0. The integral of 0 is any constant c. The derivative of any constant is 0. Thus, the integral of 0 is any constant c. And because c can be any constant, our solution is what is known as the general solution, which means that the given ordinary differential equation that we are solving by separation of variables has infinitely many solutions. For the integral of the second term, we apply the power rule. The integral of y squared with respect to y is y cubed over 3 minus y cubed over 3. We apply the power rule. We add 1 to the exponent of y. 2 plus 1 is 3. And the sum we also use as divisor of y cubed. For the second term, we apply simple algebraic substitution. By inspection, you can see that the derivative of x squared plus 2 is 2x dx. And we have x dx in the numerator. So we can, to simplify the first integral, we can use algebraic substitution and have a change of variable. We let u equals x squared plus 1. We let u equals the denominator x squared plus 1. And we differentiate both sides. Derivative of u is du. The derivative of the right hand side, derivative with respect to x, derivative of x squared is 2x dx, and derivative of 1 is 0. In the numerator, we have x dx, and we can solve for x dx from this equation by dividing both sides by 2. So we divide the left side by 2, and we divide the right hand side by 2. And 2 will cancel out from the right side. And we get x dx is equal to du over 2, or 1/2 of du. I will write du over 2. We replace x squared plus 1 in the denominator by u, and we replace x dx with du over 2. Hence, the integral of x dx over x squared plus 1 by this algebraic substitution is now x dx is du over 2. the integral of du over 2 divided by x squared plus 1 is u. And we simplify this. This is equal to the integral of du over u multiplied by 1/2. We multiply u by 2, we get du over 2u. 1 multiplied by du is du, divide by 2u. And the second term is negative of y cubed over 3 is equal to c. Now by a theorem, integration theorem, the integral of a constant times the function is equal to the constant 1/2 multiplied by the integral of du over u minus y cubed over 3 equals c. From integral calculus, the integral of du over u is ln u. And we have 1/2 in the coefficient, 1/2 multiplied by ln u minus y cubed over 3 is equal to c. And we replace now u with the original variable in terms of the original variable x. U equals x squared plus 1. We replace u with x squared plus 1. We get 1/2. 1/2 of ln of x squared. X squared plus 1 minus y cubed over 3 equals c. Now, I remove the absolute value sign because we are sure that the sum of x squared plus 1 is positive. Here, we are not sure whether u is positive or negative. That's why we have the absolute value sign. And the natural logarithm of a number exists only for positive values of a number. But since x squared plus 1 is always positive for any value of x, whether positive or negative, the ln of x squared plus 1 is defined, or ln of x squared plus 1 exists. Now we want to remove the denominators 2 and 3. So we multiply both sides of the equation by LCD, or the lowest common denominator. The lowest common denominator is the smallest number that can be divided by 3 and 2. And that number is 6. We multiply the whole equation, or multiply both sides by 6. We multiply the left-hand side by 6. And we multiply the right-hand side, the constant, by 6. We have 6 multiplied by 1/2, or 6 divided by 2 is 3. We have 3 ln of x squared plus 1 minus 6 multiplied by negative y cubed over 3 simplifies to 2 because 6 divided by 3 is 2. Negative 2y cubed. And any constant c multiplied by a constant 6, the product is still a constant. 6 multiplied by any constant is a constant, and we denote that constant by capital C. For the first term, we can apply the property of ln that says the ln of x to the n equals n multiplied by ln of x. the coefficient n here of the natural logarithm of x becomes the exponent of x. In this first term, the n here is 3. So we can rewrite the first term by raising x squared plus 1 to the exponent 3. And we get ln of x squared plus 1. The coefficient 3 here becomes the exponent of x squared plus 1 minus 2y cubed equals c. This is the general solution. The general solution of the given differential equation that we have solved by separation of variables. ln of x squared plus 1 to the power 3 minus 2y cubed equals c. For each value of the constant c, you will get a particular solution. Since we can substitute infinitely many values to the constant c, the given differential equation has infinitely many solutions, and this is what is known as the general solution. For our second example, consider the following differential equation. Solve dy dx ln x minus y over x equals 0. Again, this is an ordinary differential equation because it contains ordinary derivative of y with respect to x. And this differential equation is a differential equation of order 1 because the highest order derivative that appears in this differential equation is 1. And this differential first order ordinary differential equation has degree 1 because the exponent of the highest order derivative is 1. And to solve this differential equation is to find the equation whose derivative with respect to x will give this differential equation. And we will solve this by separation of variable, which means that if this differential equation can be solved by separation of variables, we should be able to write this differential equation in the form f of x dx plus g of y dy equals 0, which means that the coefficient of the differential of x should be a function of x only, and the coefficient of the differential of y should be a function of y only. Our first step is we multiply both sides of the differential equation by dx. We multiply the left-hand side by dx. The left-hand side we have dy dx ln x minus y over x. We multiply this by dx, or differential of x equals 0. And we also multiply the right-hand side 0 by differential of x. We apply the distributive property of multiplication over addition here over subtraction. That is, we multiply each term of the left-hand side by dx. If we multiply the first term dy dx ln x by dx, dx will cancel out. And the first term simplifies to, I will write first ln of x. ln of x dy minus dx multiplied by y, we get y dx over x. And the right hand side is 0. You can see that the coefficient of the differential of x is not a function of x only, because we have y in the coefficient of dx. To remove y from the coefficient of dx, we have to divide the whole equation or both sides of the equation by y. We divide by y. Or you can also multiply both sides of the equation by 1 over y. Instead of saying divide by y, you can say multiply both sides of the differential equation by 1 over y. Similarly, the coefficient of the differential of y is not a function of y only. We have to remove ln of x from the coefficient of the differential of y. And we can do that by dividing both sides of the whole equation by ln of x. Or you can say multiply both sides of the differential equation by 1 over ln of x. So we divide the first term by y ln of x. The first term is ln of x dy. We divide by y ln of x minus y dx over x, and we divide this by y ln of x. So x will be multiplied by y ln of x equals 0. Divide by y ln of x. Now cancel from each term the quantities that will result to 1, like ln of x divided by ln of x is 1. Hence ln of x will cancel out. And the coefficient now of the differential of y is 1 over y. Y over y will give 1. So you can cancel out y from the numerator and denominator. Now the coefficient of dx is 1 over x ln of x, which is now a function of x only. And the right hand side simplifies to 0. I will write first the term containing the differential of x. To write this differential equation in this form. We have negative 1 over x ln of x, or negative dx over x ln of x. And we write this as the second term, dy over y plus dy over y is equal to 0. Now we say that the variables have been separated because this differential equation is now in this form, f of x dx plus g of y dy equals 0, where the coefficient of dx is a function of x only. The coefficient of dy, 1 over y, is a function of y only. And the solution of this last differential equation can be obtained by integrating both sides. The first term we integrate with respect to x. The second term we integrate with respect to y, and we integrate the right hand side 0. The integral of 0 is c, and we can readily integrate dy over y. The integral of dy over y is ln of y. But for the first term, we have to make use of an algebraic substitution. By inspection, you can see that the derivative of ln of x is 1 over x dx, or dx over x, which is contained in the first term. We have dx over x, the derivative of ln of x. Thus, we let, for a change of variable, we let ln of x be equal to u. We let u equals ln of x, and we differentiate both sides Derivative of u is du. Derivative of ln of x is 1 over x multiplied by dx equals dx over x. In the first term, we replace ln of x with u. We replace dx over x with du. And we still have negative. We can actually factor out negative, and the first term becomes negative of the integral. Dx over x is du over ln of x is u plus the integral of dy over y equals integral of 0. We now integrate each term of the left-hand side and the right-hand side. The integral of du over u from your integral calculus is ln of u. And the integral of dy over y is ln of y. And the integral of 0 is a constant. Now, to make use of the properties of natural logarithm, instead of writing simply a constant c, I will write ln of a constant. ln of c. By property of natural logarithm, the ln of a over b is equal to ln of a minus ln of b. That's a property of natural logarithm. The natural logarithm of a over b equals ln of the numerator minus the natural logarithm of the denominator, and we can apply this property of natural logarithm to the left-hand side of this equation. So by this property of natural logarithm, the left-hand side now is equal to ln of y ln of y, your a now is y, your b is u. The left-hand side is equal to ln of y over u equals ln of c. We write absolute value sign because we are not sure whether y over u is positive, and it has to be positive. Similarly, for c, we write ln of c. Here now, with the absolute value, c can be any constant, positive or negative, and we take its negative, we take its absolute value if c is negative, and we get the ln of positive number. Now, we now substitute the value of u. U is ln of x. And we take the exponential of both sides to remove the natural logarithm from both sides. We now replace u with ln of x, which we use to have a change of variables so that we can integrate the first term of the differential equation after separation of variables. We now write ln of y over ln of x equals ln of a constant. Now, to remove the natural logarithm from both sides, we take the exponential of both sides, exponential of ln of c and exponential of ln of y over ln of x. And we apply another property of natural logarithm that says e to the power ln of x equals x. This is because the ln is a logarithm to the base e. Thus, e to the power ln of x simplifies to x. Again, ln is a logarithm to the base e. And this property says if you raise e to the natural logarithm of x, this simplifies to x. And we apply this property to both sides of this last equation. In the left-hand side, your x in this property is y over ln of x. Hence, the left-hand side simplifies to y over ln of x equals, the right-hand side, your x in this property is c. Thus, the right-hand side simplifies to c. Or we multiply both sides by ln of x. We should write absolute value of x equals c. Multiply both sides by ln of x, we get y equals c. Multiply by ln of x. And this is the general solution of the given differential equation. Now we will take an example where there are initial conditions given. When initial conditions given, we are looking for a particular solution. A particular solution is a solution of the given differential equations that satisfies the initial conditions given. For our third example, consider the following problem. Solve the following initial value problem. We have 6y prime equals y to the 4 multiplied by sine t. Y of 0 equals 1. This problem is called an initial value problem because there are initial conditions given. In this particular problem, the initial conditions are y of 0 equals 1. This means that when the value of the independent variable t is 0, the value of y equals 1. And for these initial conditions given, we have to find the particular solution from the general solution. Thus, the first step is still to find the general solution and then substitute the initial conditions given to find the particular solution. In this given differential equation, we are given y prime, which means that y is the dependent variable and the other variable t is the independent variable. Thus, y prime implies that y prime means derivative of y with respect to t. And we will solve this. We will look for the general solution of this differential equation by separation of variables. We write y prime as dy dt, derivative of y with respect to t. The left-hand side now is 6 multiplied by dy dt is equal to y raised to 4 multiplied by sine t. And we have to write this differential equation in which the coefficient of the differential of y is a function of t, is a function of y only, and the coefficient of the differential of t is a function of t only. First, we multiply both sides by differential of t. We multiply the left side by dt, and dt from the denominator will cancel out, and the left hand side simplifies to 6 dy. 6 dy dt we multiply by dt. Multiply this by dt. The right hand side y raised to 4 sine t we also multiply by dt, or differential of t. And dt will cancel out from the left hand side because dt over dt simplifies to 1. And for the left hand side, we get c d 6 dy equals y raised to 4 sine t dt. And the variables have not been separated yet because we still have y raised to 4 in the coefficient of the differential of t. To remove y raised to 4 from the coefficient of the differential of t, we divide both sides of this differential equation by y raised to 4. We divide the left-hand side by y raised to 4. And we also divide the right-hand side by y raised to 4. And y raised to 4 will cancel out from the right-hand side because y raised to 4 divided by y to the 4 is 1. We cancel out y raised to 4. And here we have 6 dy over y raised to 4 is equal to sine t dt. Now we say that the variables from this given differential equation have been separated because the coefficient now of the differential of y or dy is now a function of y only. Coefficient of dy is 6 over y raised to 4. From the right hand side, the coefficient of the differential of t is now also a function of the variable t only, which is sine t. And we obtain the general solution of this last differential equation by integrating both sides. The left-hand side we integrate with respect to y, and the right-hand side we integrate with respect to t. By property of integral or by a theorem for integration, the integral of a constant times a function is equal to the constant times the integral of the function. Hence, we can write the first term as 6 multiplied by the integral of dy over y raised to 4. The first term now is equal to 6. 6 multiplied by the integral of dy over y raised to 4 is equal to the integral of sine t with respect to t. Is equal to the integral of sine t with respect to t. To apply the power rule for the left-hand side, we bring y raised to 4 to the numerator, and we take the opposite sign of the exponent of y. Hence, the left-hand side is the same as 6 multiplied by y multiplied by the integral. We bring y to the 4 to the numerator. We have y to the negative 4. We integrate that with respect to y. Equals the integral of sine t dt. Now we can apply the power rule to find the integral of the left-hand side, where the exponent n in the power rule is negative 4. So we add 1 to negative 4. Negative 4 plus 1 is negative 3. And the integral of the first term is 6 multiplied by y to the negative 3. And we also use negative 3 as the divisor. Divide by negative 3. And from your integral calculus, the integral of sine t is negative cosine t. Negative cosine t plus the constant of integration c. And we still can simplify the left-hand side. We divide 6 by negative 3. We get negative 2. y to the negative 3 equals negative cosine t plus c. This is the general solution for the given differential equation. And to find the particular solution that satisfies the initial conditions given, that is the condition when t equals 0, the value of y equals 1. When we substitute these initial conditions given in the general solution, we will find the value of c. The conditions given, y of 0 equals 1. This implies that the value of t is 0. When the value of t is 0, the value of y is 1. So we replace y with 1. Again, the initial conditions given are y of 0 equals 1, which implies that when the value of t is 0, the value of y is 1. And in the general solution, we replace y with 1, and we replace the independent variable t with 0. And we get negative 2. Negative 2 multiplied by y1 to the power negative 3 equals negative cosine of t, our t is 0, plus c. We have positive 1 to the power negative 3. That's the same as 1 over 1 to the power 3, which gives us 1 multiplied by negative 2 is negative 2. Again, 1 to the power negative 3 is 1. Multiplied by negative 2 is negative 2. Or you can use your calculator to compute the value of negative 2 multiplied by 1 to the power negative 3 is equal to cosine of 0 is 1. Cosine of 0 is 1. Multiplied by negative, we have negative. Negative 1 plus c. Therefore, from this equation, the value of c is equal to negative 2 plus 1. If you transpose negative 1 to the other side, you get plus 1. Therefore, c equals negative 2. Transpose negative 1 plus 1 equals negative 1. This implies the value of c equals negative 1. The value of our constant c equals negative 1. And we will substitute the value of c in the general solution. And after the substitution, you get the particular solution that corresponds to the initial conditions given. We now substitute our value of c, which is negative 1, to the general solution to obtain the particular solution. Our general solution is negative 2y to the power negative 3. Negative 2y to the power negative 3 equals negative cosine t plus our value of c is negative 1. Or we simplify negative 2y. I will remove the negative exponent from the left-hand side by using property of exponent. Thus, y to the power negative 3 is 1 over y to the power 3. And the left-hand side simplifies to negative 2 over y to the power 3 equals negative cosine t Positive multiplied by negative is negative 1. And we factor out negative from the right hand side. We have negative 2 over y cubed equals, factor out negative from each term from the right hand side. The other factor are negative cosine t divided by negative is positive cosine t. And negative 1 divided by negative is positive 1. I multiply both sides by y to the power 3. I will now solve for y in terms of the independent variable t. So we can express y as a function of t explicitly. Multiplying the left side by y to the power 3, we get negative 2 equals negative multiplied by cosine t plus 1. And multiply the right side by y to the power 3. We can cancel out both negative from both sides of the equation, or multiply both sides of the equation by negative 1. And you get 2 is equal to cosine t plus 1 multiplied by y to the power 3. Now we divide both sides of the equation by cosine t plus 1. Divide the right side by cosine t plus 1. And divide the other side by cosine t plus 1. And cosine t plus 1 will cancel out from the right hand side, and we get y cubed equals, y cubed now is equal to 2. Y cubed equals 2 over cosine t plus 1 divided by cosine t plus 1. And we raise both sides to 1 over 3 to remove the exponent 3 from the left hand side. Or we take the cube root of both sides. We take the cube root of 2 over cosine t plus 1. Or you raise both sides of the equation by 1 over 3, or to the power 1/3. And the cube root of y cubed by property of exponent is y. And y now is equal to the cube root of 2 over cosine t plus 1. 2 over cosine t plus 1. This is the particular solution that corresponds to the initial conditions given y of 0 equals 1. That means when t equals 0, the value of y is 1. And this is the general solution. For the initial conditions given, this is the particular solution. Now we check if the initial conditions are satisfied by this particular solution. When t equals 0, we get the cube root of 2 over cosine of 0 plus 1. And cosine of 0 is 1, plus 1 is 2. So we have 2 divided by 2 is 1. And the cube root of 1 is 1, which is the given condition. When t equals 0, the value of y is 1. That is how you check if your particular solution is correct. You substitute the initial conditions given in the particular solution. Example, when t is 0, we substitute 0 for t. Cosine of 0 is 1, plus 1 is 2. We have 2 in the denominator and 2 in the numerator. 2 divided by 2 is 1. And the cube root of 1 is 1, which is the value, the initial condition given for y equals 1. Again, to solve an initial value problem, you have to find first the general solution. And from the general solution, you substitute the values given from the initial conditions given to find the constant of integration c. And then you substitute the value of the constant c to the general solution to get the particular solution. For your practice, please try the following exercises. So that means you find the general solution of each of the given differential equations, and when there are initial conditions given, you find the particular solution. In number 1, the given is 2 dy dx equals y multiplied by quantity x plus 1 all over x. You will use separation of variables to find the general solution of this differential equation in number 1. In number 2, the given is 2 dx dt minus x equals 3. The dependent variable here is x, the independent variable is t. And again, you will solve this differential equation by separation of variables by making the coefficient of dx a function of x only and the coefficient of dy a function of t only. In number 3, the given differential equation is the square root of quantity 1 plus 4x squared dy equals y cubed x dx. Applies the separation of variables to find the general solution of this differential equation. In number 4, dy dx plus 2y equals 6. And you have the initial conditions given when x equals 0, y equals 1. The first step is you find the general solution of this differential equation by separation of variables. And then substitute the initial conditions given x equals 0 and y equals 1 to find the constant of integration c. And then you substitute that value of c to the general solution to find the particular solution that satisfies the initial conditions given. Similarly, in differential equation number 5, there are initial conditions given when x equals 2, the value of y equals e. The first step, you solve this differential equation by separation of variables to find the general solution. And in the general solution, you substitute the initial values given when x equals 2, y equals e. And you substitute that value of c to the general solution to find the corresponding particular solution. The particular solution that corresponds to these initial conditions given. In the next lesson, we will apply separation of variables to RL circuit by solving the differential equations formed by using Kirchhoff's law. Kirchhoff's law. Also, we will take another application of separation of variables in finding the terminal velocity of a skydiver. If you have any questions about the lesson for today, separation of variables, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalison. Thank you.